Hello everyone, welcome to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. Our first circuit is a clipper circuit. Now clipper circuit or limiter circuit or amplifier selector circuit is actually a circuit that cuts an existing waveform. That is, let's say we have a sine wave. This is a sine wave. This is the positive half cycle of the sine wave, and this is the negative half cycle. Now, when we say about clipping or cutting an existing waveform, what we mean is we can either cut the positive half cycle of the sine wave, and we will get the entire negative half cycle, but positive half cycle will be cut, or we will get our entire positive half cycle, but the negative half cycle will be cut. Part of the negative half cycle is cut here and part of the positive half cycle is cut here, right? So this is called a positive clipper. A circuit that does this is called a positive clipper, and a circuit that does this is called a negative clipper. Okay. Now we will see how a diode does this, right? How a diode makes a positive clipper or a negative clipper. So we have already seen one classification of a clipper circuit, that is as positive clipper and negative clipper. There is also another classification that depends on the position of the diode. If the diode is in series with the source, then that clipper is called a series clipper. And if the diode is in parallel with the load, then that clipper is called a shunt clipper. So we have already seen that clipper circuits can be classified into positive clipper and negative clipper based on where the cutting occurs, clipping occurs, or we can classify them into series clipper and shunt clipper based on the position of the diode in the circuit, right? So a series clipper can be a positive clipper or a negative clipper. Also a shunt clipper can be the same, positive clipper or negative clipper, right? Now let's see shunt clipper, how a shunt clipper circuit looks. Okay, so here we have our source, a resistor, and a diode. Now there is an important thing, that is, when I showed you this picture, in this picture you can see that the entire positive half cycle was not cut in positive clipper. It was cut up to a limit, and it stays at the limit, and then it gets back to the sine wave. So there is a constant voltage called reference voltage, Vref. Here also we have a negative reference voltage, minus Vref, in negative clipper. Okay, so in positive clipper this Vref can be negative, and in negative clipper this Vref can be positive. It depends. We'll see those circuits later. Now I will introduce a Vref here, a reference voltage. This is our Vref, reference voltage. Now the clipping occurs with respect to this reference voltage. Okay, we'll see that. So this is our V in, which is Vm sin omega t, the sine wave, and the peak is Vm. There is a resistance R, this is our diode D, and this is our Vref, a reference voltage. And here we have our output. This is our V out. Now let's see how it works. We'll draw a sine wave. Two sine waves to denote the input and output. This is our V in, and here we have our V out. Okay, input is obviously a sine wave. Okay, now we know that there is a reference voltage also, so I am showing the reference voltage here. Now let's see how the circuit works, right? So here we have a diode, and as always we are assuming that our diode is ideal. So this is our assumption, that the diode is ideal. So it makes it easy to analyze the circuit. So now we want to see when the diode is turned on. That makes the difference in the circuit. Okay. So to turn this diode on, we know that the anode voltage must be greater than the cathode voltage. Since it is ideal, it must be at least 0, right? So we know that sine wave is increasing, and the cathode voltage of this diode is clamped to this voltage Vref, and anode voltage is changing with the input sine wave. So below this reference level, what happens to the circuit? The anode voltage, which is the sine wave, is this part, it is less than the cathode voltage. So obviously the diode will not turn on. So when you look at the circuit, the diode part will be open circuit. So this doesn't come into picture, and at the output we'll get the input, right? Input is directly connected to the output when the diode is turned off. So until this Vref, we'll get the output same as the input. What happens at Vref? Now at Vref, we know that anode voltage is equal to cathode voltage. So when anode voltage is equal to cathode voltage, this diode is turned on. So this is a short circuit, and our output is now directly in parallel with Vref. So what will be the output? It will be same as Vref. So when VA is from the point VA equal to VK and onwards, that is when VA is greater than VK, the output voltage remains at Vref. Now at this point, again VA equal to VK, and below that what happens? VK becomes more than VA. Again diode is turned off, right? When VK is more than VA, diode is turned off. So what will be the output? Input is directly getting connected to the output. So the output will be same as the input. Now what happens in the negative half cycle? There is no question about that, right? VK is always greater than VA, diode is turned off, and output will be same as input. This will be the entire negative half cycle. So this is what happens in shunt clippers. Okay, so this is a shunt clipper, but what kind of clipper is this? This is also a positive clipper, the positive shunt clipper. Now if we do something, it can change into a negative clipper. Think about it. You can pause the video here and think about it. What will change the circuit into a negative clipper? If you got the answer or you didn't, we'll see that. Okay, so here we have our input, again the resistance, and just changing the direction of the diode connection. This is our Vi, which is Vm sin omega t, resistance, diode, and Vref. Now let's see what happens. Again, all our assumptions remain the same. Okay, so this is our sine wave. Now this is our Vref. This is V in, this is Vref, and here we have our V out. Now let's see what happens. This is our V out. Okay, so this is the anode and this is the cathode of our diode, right? And the anode is connected to a positive supply, and which is Vref. Now anode is connected to Vref, and cathode voltage changes according to V in, right? So initially V in, which is cathode voltage, which is less than Vref, right? So what will be the output? Sorry, what will be the condition of the diode? Anode voltage is greater than the cathode voltage, that is from this point to this point. This is anode voltage changing. So from this point to this point, cathode voltage is less than anode voltage. So when cathode voltage is less than anode voltage, what happened to the circuit? This diode will be forward biased. So when the diode is forward biased, what happens to the output? The output will be clamped to Vref. So until this point, what will be the output? Output will be equal to Vref. These are Vref. Okay, what happens after that? So after this point, cathode voltage increases, right? This is cathode voltage. So, and this is Vref is anode voltage. Sorry, I made a mistake here. This is cathode voltage. So after this point, cathode voltage is more than anode voltage, and diode will be reverse biased. When diode is reverse biased, what happened to the output? Diode is reverse biased, and this is open circuit. V out is connected to V in. So we will get V out equal to V in. Now again, at this point, what happens? Cathode voltage becomes less than anode voltage, and diode is again short circuited, and what will be the output? Output will be equal to Vref. Whenever the diode is turned on, output will be equal to Vref. So this point onwards, until this point, the output voltage will remain at Vref. So this will be your output voltage. Okay, this is the V out, and this is Vref, and this part of the wave is Vm sin omega t only. Now what kind of clipper will be this? We cannot see the negative half cycle in this output waveform. That means this will be a negative clipper. This is a negative shunt clipper. And previous case was, the first one was positive shunt clipper. Now we will see what a series clipper is. Now we have seen that when the diode is parallel to the output, that is parallel to the load, this clipper is called a shunt clipper, and when the diode is in series with the source, it is called a series clipper. So we will see a circuit where the diode is in series with the source. So this is an example. Diode is in series with the source. There is our load. Okay, here you have your output. Here I haven't shown any VREF, but we can give a VREF here. So let's say we will only go with reference voltages. So this is VREF. You can give a 0 VREF, that is, this can be connected to the ground, and that will make the reference voltage 0. That's it. Okay, so this is our VREF, this is our R, this is our diode, this is anode of the diode, this is cathode of the diode, and this is V in, which is Vm sin omega t. First we will see the waveform, then we will name the circuit. Okay, again input, reference, now we need to see what the output looks. Okay, now when we look at the circuit, the cathode of the circuit is connected to VREF. We are assuming that the diodes are ideal and initially the diode is turned off. So this will be a open circuit. So in an open circuit, there is no current flowing. So this cathode potential is clamped to this VREF, right? So cathode is connected to a positive voltage VREF and anode is connected to our input voltage. Okay. Now let's see, when input is, our Vm sin omega t is less than VREF, that is up to this point, what happens to the diode? Will it turn on or will it be turned off? Now we know the answer, right? When input is, that is with the voltage connected to anode is less than VREF, diode is turned off. When the diode is turned off, what will be the output? Output is directly connected to VREF, so output is clamped to reference voltage. Right? So when the input voltage increases beyond this point, that is when anode voltage is more than cathode voltage, diode is forward biased, diode is turned on, what will be the output? Output is directly connected to the input because diode is short circuited. So output is connected to input and the output will be same as the input. And up to what point it will go? Up to this point. After this point, again the anode voltage falls below the cathode voltage and output voltage is again clamped to the reference voltage, and during the entire negative half cycle this goes on. So this is the output of our circuit. So looking at the output, we can now name the circuit, right? What will be the name of the circuit? Our negative half cycle is not visible, that means this is a negative clipper. Since the diode is in series with the Vn, this is a negative series clipper. Now I leave one job to you, that is you have to find the circuit for a positive series clipper, and that job is left to you. By looking at these two circuits, you might have got an idea how to do that. Okay. Now we have to see some characteristics of this circuit, and those characteristics are called transfer characteristics. Transfer characteristics. Transfer characteristics are basically a graph between input and output. So on the x-axis we have V in, on the y-axis we have V out. So what was our first case? It was positive shunt clipper. So we'll see the transfer characteristics of positive shunt clipper. Now when we look at the circuit, we can see that up to Vref the input is same as the output, right? Up to Vref input and output are same, and when input is equal to Vref, output becomes equal to Vref, right? So let's say this is our Vref. Again here also we have Vref. So up to Vref input and output are the same. So as input changes, output also changes. A linear relationship, input and output are the same. When input reaches Vref, what happens to the output? Output becomes clipped and output is set to Vref. Until then the slope is 1. And during the negative half cycle, you know that V in is equal to V out, right? During the negative half cycle, V in is equal to V out. So this will be the transfer characteristics of a positive shunt clipper. Now our next case was negative shunt clipper, right? So negative shunt clipper. Again the characteristics between input and output. Here we have our V in, here we have our V out, and here we have our Vref. Okay. Now when we look at the circuit, this is the negative shunt clipper. When V in reaches, this is V in going up to Vref. When V in is going up to Vref, output is equal to Vref. That is, when V in reaches this up to this point, the value of output will be equal to Vref. And what happens after Vref? After Vref, V out is equal to V in, right? After that, V out is equal to V in. So this is Vref, and here the slope is again 1. What happens in the negative half cycle? In negative shunt clipper, whatever we do in the negative half cycle also, the output is clamped to Vref, right? So when V in is negative, then also the output is clamped to Vref. So this is the transfer characteristics of a shunt clipper, negative shunt clipper, and on the left we can see the transfer characteristics of a positive shunt clipper. Now if you look at the output voltage of positive shunt clipper, negative shunt clipper and negative series clipper, you can see that the output looks the same, output voltage looks the same, right? That means negative series clipper also has the same characteristics, same transfer characteristics as negative shunt clipper. Similar way, positive shunt clipper and positive series clipper will have the same transfer characteristics. Okay. Now our next circuit is called slicer circuit. Actually, this is a two-level clipper circuit. Now let's see how a slicer circuit works. We have our input, resistance, and diode is connected to a reference voltage. Another diode which is connected to another reference voltage. Here we have our output. So this is our slicer circuit. This is diode D1, diode D2. This reference voltage is VR1. This reference voltage is VR2. Okay. Before getting into the working of the circuit, we are assuming that diodes are ideal as usual, and VR2 is greater than VR1. This is the condition here. VR2 is greater than VR1. Now we can look at the input and output voltages. This is our input voltage, sine wave. There are two reference voltages, VR1 and VR2. Okay. This is VR1 and this is VR2. Okay. Now we can analyze the circuit and see what output voltage looks like, right? Okay. Now this is the zero voltage. Now we know that the diode D1 is, its anode is connected to VR1. This is the anode. It is connected to VR1. So until the input voltage reaches VR1, this diode will be turned on, right? That means until this voltage becomes equal to or just greater than VR1, this diode will be turned on because the anode voltage is more than the cathode voltage. When this diode is turned on, what will be the output? Output will be equal to VR1, right? So until our sine wave reaches VR1, that means until this point, that is, let's call it point A. Until point A, what will be the output? Output will be equal to VR1. Let's call this point B. So what happens between point A and B? So when voltage is above VR1, then the cathode voltage of diode D1 is more than the anode voltage. Diode D1 is turned off, right? Also, diode D2 has a cathode voltage equal to VR2. Until the anode voltage reaches VR2 or just greater than VR2, diode D2 cannot be turned on. Between point A and B, we have the input which is between VR1 and VR2. When the voltage is between VR1 and VR2, both the diodes are turned off, and what will be the output? Output will be same as the input. Output will be same as the input, the sine wave, right? And when the input voltage Vi reaches VR2, the anode voltage of diode D2 will be equal to VR2, that is the cathode voltage, and diode D2 will be forward biased. When diode D2 is forward biased, it is short circuit and output is connected to VR2. So what will be the output? It is clamped to VR2. Okay. So between again sine wave and below VR1 will again get VR. So this repeats every cycle. So this is VR. So this is a slicer. A slicer circuit can be used to generate asymmetrical square waves. That circuit I can show here. The resistance, our first diode, and its reference is now negative. Second diode with a positive reference voltage. Here we have our output. D1, VR1, which is actually a negative voltage, D2, VR2. Okay, resistance R, this is V in. Now if we look at the voltage waveforms, this is V in, this is V out. VR1 is now a negative voltage, VR2 is now a positive voltage. Let's say their magnitudes are same. This is VR2, this is VR1. Okay. Now when we look at the circuits, so when we look at the circuit during the positive half cycle, we'll look at D2, because during the positive half cycle D1 cannot be turned on because the anode of D1 is connected to a negative voltage. Cathode voltage is never going to be less than the anode voltage during positive half cycle. So during positive half cycle, we don't have to bother about diode D1. During the positive half cycle, when we look at diode D2, until the input voltage reaches VR2, diode D2 will be off because the cathode is connected to VR2. So anode voltage is the input voltage, and until input voltage reaches VR2, diode is reverse biased and it is turned off. Until Vin reaches VR2, diode D2 will be reverse biased, so it is an open circuit, so Vout is directly connected to Vin. And when Vin reaches VR2, what happens? The anode voltage of diode D2 is now equal to VR2, which is the cathode voltage. So diode will start conducting because it is an ideal diode. It conducts at zero bias, and output will be equal to VR2 because diode will act as a short circuit. Again, after this point, sine wave is less than VR2, and we will get the rest of the output as sine wave, right? When we look at the circuit in negative half cycle, diode D2 will not be turned on. Let me redraw this. Diode D2 will not be turned on, right? When the voltage input is negative, diode D2 will not be turned on. So we only look at diode D1. So now Vin is negative. So there we have our VR1. So when Vin falls below VR1, that is when the diode will be turned on. Diode D1 will be turned on. So the anode voltage of diode D1 is connected to minus VR1. So until the cathode voltage is below this level, diode will not be turned on, and when the cathode voltage is below this level, that is at this point onwards, we will get our diode turned on. So when the diode is turned on, what will be the output? Output will be clamped to minus VR1. Until this point, this clamped to minus VR1, and when the input voltage falls below minus VR1, that is when we are talking in magnitude terms, again we will get the output as same as the input. So this will be the output of this particular case. Okay, so this is VR2 and this is VR1. Our next circuit is called a peak detector circuit. So the circuit diagram is like this. We have a input voltage, then a diode in series with the source, and a capacitor. This is Vin, which is Vm sin omega t, diode D, and capacitor C. Our output, we will see what the output looks like. Okay, this is the output terminals. This is our input. Now what happens is, during the positive half cycle, diode is turned on, as we know that. So we will assume that the diode is ideal. So from 0 volt onwards, the diode is turned on. When the diode is turned on, it will act as a short circuit and the capacitor will get charged. Now when the capacitor will get charged, we know that the capacitor voltage will be same as the input voltage. Capacitor voltage will increase just as the input voltage is increasing, and then it reaches the peak V max, this Vm sin omega t. This is Vm. So when the output voltage reaches, that is the capacitor voltage reaches Vm, what happens is, now this is Vm, right? Now the cathode of the diode is connected to Vm and the anode voltage is about to go below Vm, right? So cathode voltage is connected to Vm and anode voltage is just below Vm. And what happens to the diode? The diode will be reverse biased. When the diode is reverse biased, what happens? The capacitor doesn't have a charging circuit or discharging circuit anymore connected to it. So the capacitor voltage will remain the same. Capacitor voltage will remain at Vm. Okay. So when the input voltage is just below Vm, diode is reverse biased, and when diode is reverse biased, it is open circuited, and now the capacitor is connected to an open circuit. Usually there will be some load connected here, but we are assuming that there is no load connected. This is an open circuit case. So the capacitor voltage will be now equal to Vm. So V out is equal to Vm. So we have detected the peak. When input reaches the peak, our output will go to peak voltage. So there is another circuit that uses this concept to generate particular waveforms, and that circuit is called a clamper circuit or a DC restorer circuit. What clamper circuit does is that it will add a DC voltage level to our existing signal, or it will clamp a DC level with our existing signal. Depending on the level of the voltage that is getting clamped, whether it is positive or negative, clamper circuits are divided into two, and they are positive clamper and negative clamper. Okay, first we will see how a positive clamper circuit works. So this is the circuit. Here our Vn is equal to Vm sin omega t. Okay. Now when we look at the circuit, we can see that this is similar to the previous circuit, but only the position and direction of diode and capacitors are changed. So we'll look at it from a we'll begin with a negative half cycle. So what happens during negative half cycle, that we have to see. Okay, so I'm not denoting anything here. So during the negative half cycle, we know that this point is more positive compared to this point. So this diode will be forward biased, and when the diode is forward biased, this capacitor will get charged. So the charging direction will be like this. Charging current flows like this. So diode is now short circuited, because as usual we are assuming that the diode is ideal. So when the diode is short circuited, the capacitor is getting charged. So we know that the capacitor will get charged until the voltage is Vm. The capacitor voltage is Vm. When the capacitor voltage reaches Vm, the cathode of this diode is now connected to plus Vm, and anode voltage is now going to be below Vm. That means the diode can never be turned on again unless the capacitor discharges. Okay, there is a condition. Now if the capacitor doesn't discharge, if we don't use any load here, if we are simply saying that it is open circuited, now the diode is never going to be turned on, right? Now when the diode is on, we know that is when the diode is on, we know that V out will be equal to 0, because V out is the voltage across the diode. When the diode is turned on, the voltage across it is 0, because it is short circuited. So we'll see when the diode is off, that is when the diode is reverse biased. On means forward biased. So when the diode is off, meaning reverse biased, on means forward biased, you know this. So when the diode is off, what happens to the output voltage? Now we have a open circuit here. So output voltage will be, so let me change this, because this is not the actual direction of V in. We can say that this is the actual direction of V in. So when the diode is off, it is open circuited. So when the diode is open circuited, what will be the value of Vout, Vout will be equal to Vin plus the capacitor voltage, which is now clamped to Vm. So we know that Vin is Vm sin omega t. So output is Vm sin omega t plus Vm. So during the first half cycle, this happens. Initially the diode is turned on, capacitor is charged. When the capacitor is charged to Vm, diode is turned off. Now when we look at the circuit, we are going to look at the circuit when the diode has, when all this process has been completed. That is, capacitor is already charged to Vm and that particular full cycle has been completed. Okay. So now our output is this case. Now diode is never getting turned on. So our output is Vout is equal to Vm sin omega t plus Vm. So if we draw the output waveform, it will look like this. This is Vin, this is Vout, Vin is a sine wave, and now we know that Vout is equal to Vm sin omega t plus Vm, that is Vin plus Vm. So every point on Vn is now raised to a level which is Vm. So the 0 is raised to a level which is Vm, right? So now this is our Vm. Every point is now raised to this Vm. When 0 is raised to Vm, that is when Vin is equal to 0, what will be Vout? 0 plus Vm. So it will be Vm. When Vin is equal to Vm, what will be Vout? Vout is equal to Vm plus Vm, which will be 2Vm. When Vin is equal to 0 again, I will draw this as well. When Vin equal to 0, Vout is equal to Vm. When Vin equal to Vm, Vout is equal to Vm plus Vm, which is 2Vm. Again Vin is equal to 0, that means Vout is equal to Vm, right? Then when Vin reaches minus Vm, Vout will be 0. Vout reaches 0. Let me redraw that. So when Vin reaches minus Vm, what happens to Vout? Vout will be minus Vm plus Vm, that is 0. Again it goes back to Vm. So this is the output voltage. Now it is like this. Its minimum value is 0 and maximum value is 2Vm. Okay. Now we can see how a negative clamper works. So this is the circuit of a negative clamper. Vout, Vin, capacitor and diode. Okay. So we know that during the positive half cycle, diode will be forward biased. So diode is turned on. When the diode is turned on, the capacitor is going to be charged to Vm. When the capacitor is charged to Vm, the diode is now turned off, right? So when the input voltage falls below the value of Vm, what happens to the diode? Diode will not be turned on. Condition is the capacitor shouldn't be discharged. Okay. So when the diode is forward biased, Vout is equal to 0, right? Because Vout is now across the diode. When the diode is turned on or forward biased, Vout is equal to 0. When the diode is reverse biased, what will be V out. When the diode is reverse biased, it is an open circuit, so there is V out, and the value of V out will be V in minus Vm, right? You can apply KVL here and find out this value. V out will be V in minus Vm. So initially in a half cycle, in a full cycle, we are not considering the first full cycle. In the first quarter cycle, the capacitor has already charged to plus or minus Vm and the diode has already turned off. We'll see the cycles after steady state. Okay. So let's say steady state has already reached. This is our input. This is our output. Okay. Input sine wave. So in the negative clamper, the capacitor is now clamped to a negative voltage, and that negative voltage is equal to Vm. Okay, so let me show Vm here. This is Vm. So we know that V out is equal to V in minus Vm, which is Vm sin omega t minus Vm. So initially the value of Vm sin omega t or V in is 0. So what will be the output voltage? It will be, this is minus Vm, sorry, this is 0. So this is minus Vm. So the output voltage will be 0 minus Vm, which is minus Vm. Then the input is sinusoidally increasing to Vm. When the input voltage reaches Vm, which is this point, what happens to the output voltage? It is Vm minus Vm. So it is sinusoidally increasing to 0. Vm minus Vm is 0. Then input voltage again decreases to 0. When input voltage reaches 0, what will be the output voltage? 0 minus Vm. So at this point, we'll again get minus Vm. Okay. Then input voltage is now minus Vm. When the input voltage reaches minus Vm, what happens to the output voltage? Minus Vm minus Vm. That will be minus 2 Vm. So output voltage increases in the opposite direction to minus 2 Vm, and again when the input voltage reaches 0, it is sinusoidally increasing to minus. So this is the output voltage of a negative clamper. If we say in terms of magnitudes, minimum magnitude is 0, maximum magnitude is 2 Vm. Okay. So this is a negative clamper. With that, we have already seen different diode circuits. We have some more diode circuits to discuss, and before that, we'll do some problems. So this is our first problem, that is, we have a circuit shown here. This is the reference potential. If V in equal to, this is V in equal to 5 sin t, what will be the shape of the output voltage in the circuit shown below? And we can assume that the diodes are ideal. So the diode is there is a 2 volt supply connected in this circuit, the resistance and a diode. Okay. Now we can do the problem. You can pause the video here and you can try this problem by yourself. This comes under clipper circuits. Okay, let's look into it. The input voltage, we know that the input voltage is V 5 sin t. We need to find the shape of the output voltage. This is V in. We know that it is 5 sin t, so maximum value is 5 volt, right? Okay. Now we are assuming that initially the diode is off. Initially the diode is reverse biased. When the diode is reverse biased, it will be open circuited. So we will redraw the figure. This is our 2 volt, and now the diode is off. This is V out. This is the anode of diode. This is the cathode of diode. This is 2 volt. This is V in. Now, what will be the anode voltage of the diode? What will be the value of VA? We can find out that, right? We can apply KVL here in this loop. So this is VA with respect to ground. So we can find out the value of VA. So VA will be V in minus 2 volts, right? VA will be V in minus 2, and VK will be equal to 0. So this is the initial case. From this case, we can see that Vk is already 0. That means if Va is greater than Vk, our diodes are ideal. That means if at least Va is equal to Vk, that means the diode is forward biased, right? So if Va equal to Vk, that is our condition for forward bias. So we can write condition for forward bias as Va greater than or equal to Vk. That means V in minus 2 must be greater than or equal to 0 volts, or V in must be greater than or equal to 2 volts. So when V in is greater than or equal to 2 volts, our diode is on, right? So when the diode is turned on, what will be the value of V out? So the first condition is until the voltage is V in is equal to 2, the diode is not getting turned on. So until this point, our output will be 0. Okay, and also after this point also output will be 0. So what happens in between these 2 points? This point and this point. Okay, that is the input voltage is greater than or equal to 2 volt. So we know that when input voltage is greater than 2 volt, our diode is turned on, so it will act as a short circuit. Now what will be the output voltage? You can apply KVL here, and we can find out the value of output voltage. So V out will be equal to V in minus 2 volts, right? V out will also be equal to V in minus 2. When the diode is turned on, when it is forward biased, that is when V in is greater than 2 volt, so it is a short circuit. When it is short circuit, V out will be equal to V in minus 2 volt. We can apply KVL here, right? So V out is equal to V in minus 2 volt. So when V in equal to 2, what will we get? V out equal to 0. When V in equal to 5 volt, V out will be equal to 3 volt, right? So from this point onwards, we will get a sine wave, and the shape will be sinusoidal, but the peak will be 5 minus 2, which is 3 volt. So this is the shape of your output voltage. Now we will meet with more problems and more circuits in the next class. So in this class, we have seen clipper circuits, slicer, and clamper circuits. In the next lecture, we will see rectifier circuits and a few more problems. Okay, until then,